Okay, we are back, and we've been talking about all sorts of fun things, and I thought we would continue today. And one of the things that we've been talking about is transformation on random variables. And we just concluded the one-dimensional case. There's also two-dimensional random variable transformations, and I don't think we're going to have time to get into that, but there is two-dimensional random variable transformation, and we will get into two-dimensional transformations here pretty quickly, and maybe we'll have times for some transformations in two-dimensional random variables, although I don't think that that's on the syllabus. So with that, let's look at the homework. And anybody have any questions on the homework? Did you do okay on the homework? Theo has hesitations.
Yes, I had a question on the first one, and I think Adam and Matthew, who I talked to, have this question as well.
Okay, let me go ahead and share the screen so we can figure out what it is here.
Okay.
Okay, it's this one, correct?
Yes. Show that G of x equals capital F of x transforms continuous F of x RV,
yes.
A random variable. Is the capital F of x supposed to be related to the lowercase f of x?
Yes, it is.
By the cumulative, like one is the derivative of the other?
Yes.
Okay.
And that's kind of weird because you're usually thinking about little g as independent of all that other stuff, right? That you kind of treat your g's, little g's in one domain, you keep your f's in the other domain, but here we're mixing and matching them. But don't forget that little f and big F are known functions, right? They are known functions, so we can use them as functions already. So yeah, this is the idea that I wanted to portray. And basically the idea is of this, and it's kind of curious. It means that if we have a random variable here, okay, I'm going to do this, and put x here and x here, and this is f sub x of x. And then we have a g of x Don't forget that there's nothing wrong with setting g of x equal to capital F sub x. That's totally righteous. And we know that this is a strictly increasing function, correct? So therefore, we can apply that formula that we derived for the strictly increasing function, or the strictly increasing function. And let's see what happens here. We get a little piece here, and this little piece is going to come up here and transfer over to here. And we're going to have on the side, this is y is equal to g of x. And then if we look on the side, we have y, and we have f sub y of x. We'll notice something which is really interesting. We know that the cumulative distribution function goes asymptotically from 0 to 1, right? So whatever that mapping is going to go between 0 and 1. There's going to be no mapping for y is greater than 1, right? Or y is less than 0. You can just see it doesn't bounce off there. And so what we wanted to show is that this transforms to a uniform random variable when little g is equal to big sub f. Did anybody get this? Okay, nobody got it. Okay, so well, let's look at the transformation. I think that f sub y of f sub y of op y is equal to f sub x. This is the first formula that we derived of g inverse of what? Of x, of y, I'm sorry, g inverse of y divided by the derivative of the inverse with respect to y. Is that right? Okay, nobody remembers that. Well, this is the formula that you use. And if you use big capital F, as you use big capital F for this, you can see that the G's manifest itself as does the X. We could also write this as, remember at the last formulation, this was just F sub X of X equal over dx dy. This is a magnitude in general, but we don't have to worry about the magnitude here because it's strictly increasing. And so the derivative is equal to 0. And then one of the other things we showed that will help in this derivation is that dy dx is equal to 1 over dx dy, right? At least engineers can say that. I think mathematicians might have a little bit more problems doing that. Well, what is dy dx? Dy dx is nothing more than d sub f sub x dx, which is equal to the density function, of course, right? But the way to work this is you can't apply the formulas. But one of the cool things to do is to literally, let me erase this. And ask ourselves, what is f sub y of y? That's the probability that y is less than or equal to y. That's the definition, right? So we can put little dots here to say is equal to, by definition, this problem. And that's equal to the probability that g of x, which is equal to f sub x of x, is less than or equal to y. Whoops. So this is the probability that capital X is less than or equal to f sub x inverse of y. And hopefully with this plethora of hints that I've given you, you'll be able to work this out. Let me go one more step. This is so this is f sub x evaluated at f sub x inverse of y. Isn't that right? In other words, and here's where it gets a little bit confusing with notation. This is the definition of the distribution function for x. Is that correct? So if instead of x here, instead of x, let me try to do something different here. Instead of x here, we have f sub y of y. I mean, this equation, and this equation are exactly the same, except that little x is equal to f sub x inverse of y, correct? The answer is yes. And what happens if we get f sub x, what happens if we get a function operating on its inverse? It's like the log of e to the x, right? We get back the original function. If we operate on a function by its inverse, we get back y. So therefore, it says that f sub y of y is equal to y. Now you're going to have to do some explaining here and explain why that this cannot go above 1 and it can't go below 0. So this inversion actually is just for the interval from 0 to 1. And I won't tell you how, but you should be able to look at the problem and determine that this is the case. Well, if this is the distribution for y, what's the distribution for, or what's the probability distribution? Whoops. The probability distribution is the derivative of this, right? What's the derivative of that? 1. So take a look at that and see if you have any questions or you would like more elaboration.
That question makes a lot more sense now. Thank you.
Okay, good. Okay, good. And I think a lot of it is just getting the right approach on it. And I think that this gives you the right approach. Okay, well, it looks like my stop screen has moved. There it is. Okay, let me get then the homework problem back up, the homework problems back up, and ask if you have any questions on those. Okay, so we've looked at this one, right? And then the question is, what happens if this becomes a discrete random variable? You don't have the pretty distribution. You don't have the smooth continuous function, but you have Dirac deltas mapping to Dirac deltas. Do you remember that? We said that for discrete random variables that you just had deltas bouncing off of that G function to give you the deltas in the y-axis. Now, show that the inverse of f of x transforms a continuous random variable into f of x. This is, I would probably ask you to approach that using the same technique that we did in the previous problem. And then also what happens if it's a discrete random variable. Okay, did anybody get this f sub y? What did you get as an answer? Those are shaking your head. What type of distribution did you get?
On the slides, it was said that it's like a Cauchy.
Yeah, it is a Cauchy. That's right. Oh, it says it on the slides. Okay.
Yeah, I get something similar to a Cauchy, like this shape.
Okay.
So, yeah, sorry.
Okay. Did you get the formula for it, though?
Yeah, here it is.
1 over pi secant squared?
Yes.
No. It should be a righteous Cauchy. It should be a constant over 1 plus x squared, or a constant plus x squared. It should have a Cauchy distribution. Did you get it? Who got it?
I don't know. I got something like that. I got 1 over y squared plus 1.
Yeah, there you go. It's a 1 over y squared plus 1. That's a beautiful Cauchy distribution. Are you able to share what you did?
I didn't expect to have it in PDF form yet today, so
okay. Well, I tell you what, let's be prepared for everybody for next time. Okay, next time it's going to be Thursday. And then this one. Anybody get this one? The first one's easy. It's just a folded Gaussian. The second one is going, I believe, if I'm right, it's going to give you a distribution which is familiar. And then the next one is literally a variation on this uniform to Cauchy. If G gives you a transformation on uniform to Cauchy, then G inverse is going to give you a transformation on Cauchy to uniform. So if G maps X to Y, then G inverse maps Y to X. So if you go from uniform to Cauchy using a G, you can go from Cauchy to uniform using the inverse of G. And so hopefully that should help you. So it doesn't seem people are prepared. And for those of you who are watching, we just had a catastrophe which shut down Baylor for a long time. So we will extend that to next time. Okay. So be prepared to have it on your PDFs and such. And we'll give an excuse because of the weather conditions. It had a big snowstorm and it shut down everybody here for a long while. Okay, any other questions or comments on the homework? Okay. Then in that case, let's go ahead and continue with our lecture. And our lecture is on characteristic functions. Characteristic functions are cool. If you remember, I started this out by asking the great mathematician and optical processor guy, Adolf Lohmann, who invented computer-generated holograms, ask him what he did to be creative. And he said, when I don't know what to do, I take a Fourier transform. And that's exactly what we're doing here. It turns out that the characteristic function is defined as the Fourier transform of the density function. Now, we've been talking about expected values. So in terms of expected values, it's e to the expected value of e to the j omega x. And I hate omegas, but I'm going to use it because that's used predominantly in the probability literature. And it's the same omega that you're familiar with. Now, it turns out that you're probably familiar with Fourier transforms in terms of linear system analysis, but the Fourier transform is a tool. And it's just like there are concepts we have in electrical engineering that are applicable everywhere. There's cases of mathematics which are applicable everywhere. For example, a parabola. You know, a parabola is the shape that you get if you throw a ball in the air, right? You get a parabolic shape. But also, if you ever go into a hotel room and they have lampshades with a bulb in it, you'll notice that the light pattern which is cast on the wall is also a parabola. Why is that? Because a parabola is a slice of a cone. It's a conic section. And if you have a lampshade, it usually spits out kind of a conic sort of light beam. And that conic light beam, when it intersects your wall, gives a slice of that cone, which is a parabola. So we see parabolas everywhere. So just because you're familiar with it as a ball thrown up in the air doesn't mean that that's the only place in the world that parabolas occur. No, they occur everywhere. And Fourier transforms occur everywhere. They occur in nature. They occur in systems analysis, where we in electrical engineering are usually used to taking time domain functions and transforming them into the frequency domain. That's usually the way that we think about it, but it's also applicable everywhere. So this is another manifestation of the Fourier transform. The cool part is that all of the theory that you've used in Fourier transform is applicable here. And if you were a math student which came in without the electrical engineering background in Fourier transforms, I'd have to take a couple of lectures to introduce you to the Fourier transform. But you guys know the Fourier transform. You should be friends with it because it's one of the most ubiquitous tools in the area of electrical engineering. In fact, in general mathematics, I would say that Fourier transforms is number 2 of all the mathematical tools that's applied. And the number 1 tool which is applied is the differential equation. Differential equations and partial differential equations. They're ubiquitous. They're everywhere. So those are the biggest tool, I think, in the sciences and in mathematics. And I think the Fourier transform probably comes in second as a mathematical tool, a form to express ideas in. So again, it can be expressed as an e to the j omega x. the expected value of that. But when you write out the expected value of that, you get e to the j omega x times the density function. And that we see is the Fourier transform. Now, you'll notice a couple of differences. Notice that we use omega and we also use j. Now, you in electrical engineering are used to using probably a minus j. So there's a little bit of change there. Instead of a j, instead of a minus j, it's a j, right? But I think that things are pretty much the same, and you just have to be careful when applying theorems to make sure that you know we have a plus j instead of the minus j that we're used to listening to. First of all, the properties of the Fourier, of the characteristic function is that the value at the origin is equal to 1, because if you take this and you set omega is equal to 0, you get e to the j 0, which of course is 1. And what you end up with is the area under the density function, which is 1, right? So the value of the characteristic function at the origin is always 1. There's another cool thing in that we can use the characteristic function to generate moments. I think I talked about this last time, but very, very quickly, if we had a phi sub x of omega equal to the Fourier transform here, and we took n derivatives of it, we would obtain, of course, okay, as engineers, when can we move the d omega inside the integral sign to operate on the integrand? The answer is always, okay? We don't worry about such things as that. But if we take this derivative operator inside the integration limits to operate on the integrand, the only thing that's a function of omega here is this e to the j omega x. So we differentiate this n times, and that gives us jx to the nth power. And this is the same thing as, I'm going to do a quickie on you. I'm going to take j to the n. Well, no, I'll just take j to the n outside. I'm not going to do the quickie on you. And what is this? This is the derivative, the nth derivative of the characteristic function evaluated at 0. In other words, I take all these derivatives, and anytime I set omega 0, I get rid of the Fourier kernel, don't I? That e to the j omega x goes, whoop, it disappears into 1. And so we have x to the n here, forgot my x to the n. And so we have this result.
Works?
Yes.
Oh, never mind. You fixed it.
Okay. Okay. Now, here's something which is kind of cool. Do you know that minus j is equal to 1 over j? Is that right? Right. So therefore, we can take this. We can take this this j to the n to the other side, and say that minus j to the n times the derivative, the nth derivative of n of phi sub x of 0 is equal to the expected value of x to the n. And I remember going through this before with you, because I remember pointing out that this n should not be a subscript, it should be a superscript. It should be the nth moment, which we can also write as x sub n. We have two ways of writing expected values, putting an e in front of it or putting a line over it. Either way is an equivalent way to express the expected value. Okay, any questions on that then? Here is a cool result. And before putting that cool result, let me just show you a theorem that we should have known. If X and Y are independent, then the expected value of G of X times H of Y, where G and X are arbitrary random variables, is the same thing as the expected value of G of X times the expected value of H of Y. Now I want you to look at that for a second and ask and see if there's any questions. I'm not sure of how obvious that is. Take a look for a second and tell me if you'd like me to elaborate on it. And if not, I'll just plow on. I will take the time to avail myself of another cup of coffee. Using boil before use McGregor, Texas water. Okay, so that looks familiar to you? Well, indeed, if that's the case, if that's familiar with you, then you should be able to see that the expected value, and this is really kind of cool, the expected value of X plus Y of omega. In other words, we're adding two random variables together. That's equal to the expected value of e to the j omega X plus Y. Which of course can be broken into two pieces. And then by our theorem, this can be written as the expected value of e to the j omega x times the expected value of e to the j omega y. If they are independent. So I will put if independent here. If they're not statistically independent, you can't do that. But if they're statistically independent, you can do that. Well, you see what we've done. This one is phi sub x, and this one is phi sub y. So it turns out that if you have independent random variables, then the characteristic function of their sum is equal to the product of the characteristic functions. That's really interesting. The characteristic function of the sum is equal to the product of the individual characteristic functions. Now, why is that so cool? Well, in electrical engineering, we know that if we multiply in the frequency domain, what do we do in the time domain? In the other domain, we convolve, right? We convolve. And indeed, that's what happens when you add two random variables together. And this is the first time we've ever been able to see this. If we inverse Fourier transform this expression, we get that the density function of the sum of two random variables is equal to the convolution of the two random variables. So when you add random variables, you convolve their probability density function. So let me give you an example of this. This is very, very interesting. Suppose that I roll a die. Here's the probability density. If I make these Dirac deltas, each of these will have an area of 1/6. But this would be the outcome. This would be the probability density function according to the output of the roll of a single die, right? They're all equally probable. Is that okay? Now what we're going to do is we're going to look at the probability of rolling 2 die. And let's look at that. We know that the smallest we can get is 2. Uh-oh, I didn't leave myself enough room, did I? I'm just going to make it over here to the 12, okay? Okay, what's the probability of getting 2? Anybody?
One
136.
1/36, right? What's the probability of getting a 3? You can either get a 1 or a 2 or a 2 or a 1. What's that?
236.
236, right? We start to see a pattern here that this kind of goes up by 1 until we get to 7. 7 is the most common output when you roll 2 die. And there's all sorts of possibilities. There's a 1 and a 6, a 6 and a 1, a 2 and a 5 and a 2, and a 3 and a 4, and a 4 and a 3. So that's 6 possibilities, right? So that's 636 here. Oh, no. Well, I guess I get a chance to redraw it, don't I? I have no idea what happened there, guys. Sorry. Ah, there it is. The Lord giveth, I guess, and the Lord taketh away. Okay. So we are good. And I want you to know that 12 comes back down to what? 1/36th? I'm not even going to go near the 12 because when I do, it changes the screen. Okay. So that's what the probability density function for the sum of 2 dies is equal to. Is that right? This is 1 die. Dig back into your undergraduate education on convolution. Does the convolution of that rectangle give you that triangle in the bottom? It does, doesn't it? So we can see here maybe your first example of the idea when you add 2 random variables like the outcome on the pips of 2 rolled die, that's equal to the convolution of the underlying probability density function. That is really cool. So if you add 2 random variables, you convolve their probability density functions if the random variables are dependent. That's a big if, of course. Okay. This is the foundation of the central limit theorem, which we will talk about soon. I've alluded to the central limit theorem. I think one of the most important mathematical properties that with use in mathematics. If you convolve a rectangle with itself, you get a triangle. If you convolve a triangle, if you convolve this with itself 3 times, you get something which is piecewise quadratic. And already you're starting to look like a Gaussian. And it does turn out that if you convolve enough functions with themselves or with other functions even, that in the end, you're going to get a Gaussian. That's really an interesting property of convolution, is that you get a Gaussian. That's the foundation of the central limit theorem. Now, this doesn't apply to all functions. It turns out that if the function has a mean and it has a standard deviation, finite mean and finite standard deviation, that the central limit theorem apply. But if you do something without a mean and a standard deviation, like the Cauchy or the Pareto, the central limit theorem doesn't apply. But if it has a mean and a standard deviation, then it does apply. And you can see that the uniform does have a finite mean, it does have a finite variance, and we do see that it applies here. So we will be talking about the central limit theorem later on in the course. It's just a beautiful, beautiful result. That's the reason that in statistics, you hear about chi-squared tests and F-squared F tests and things of that sort. They're all under the assumption that the underlying random variables are Gaussian. Why can you assume that they're Gaussian? Because if you do an average, which is adding up a bunch of numbers, your final result will probably be distributed as a Gaussian. And so therefore, this is, it always isn't true, but man, when it is true, you can get some good things. The other challenge with the central limit theorem is that if you have to add up a lot in some cases to get a Gaussian. And many times you don't have enough to get a Gaussian. It goes provably asymptotically to the Gaussian, but many times you don't have an unbounded number of numbers to add, and it's pretty close to a Gaussian, but not exact. But we'll talk about that as time goes on. Really, really fascinating result here. And we are first introduced to it, getting back to the root of the lecture, we're first introduced to it using the idea of the characteristic function, and that adding two random variables corresponds to a multiplication of their characteristic function if the random variables are independent. That corresponds to a convolution in the probability density domain. So that's one of the cool uses of the characteristic function, as we'll see. Now, how many remember, what was it? What was it? Tolkien. What did he write? Lord of the Rings, right? Remember The Hobbit? There was breakfast and second breakfast. Well, there's a characteristic function and the second characteristic function. The second characteristic function has interesting properties, and apart from the characteristic function, and here it is. The second characteristic function is simply the logarithm of the characteristic function. It's the logarithm of the characteristic function. This is very interesting. One of the things about the characteristic function is that in order to compute the variance, you have to compute the mean, then you have to compute the second moment, then you have to subtract the square of the mean from the second moment in order to get the result, right? Remember that the variance of a random variable is equal to the second moment minus the square of the first moment. Hopefully you remember that. So with the second characteristic function, you don't have to do as much work. One of the things is that the following, which is that the derivative of the second characteristic function, let's look at that. Whoops, that should be an omega, is equal to the derivative of the logarithm of the first characteristic function, right? Correct? And if you remember the definition of the logarithm and then apply the chain rule, this is phi prime of omega over phi of omega. Is that okay? Hopefully remember that simple derivative. Now, what happens if you evaluate this at the origin? Well, you get phi sub prime of 0 divided by phi of 0. And we said that this was j times the expected value of x. You remember that first derivative? And what is the characteristic function at the origin? We said it was always equal to 1, remember? So this turns out to be j times the expected value of x. So the derivative of the second characteristic function of the origin is equal to j times the expected value of x. Isn't that cool? So it's very similar to the first characteristic function. Where the magic happens is in the second derivative. The second derivative, I don't know if you remember your quotient, but it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. Whoops, this should be omega, sorry. Do you recall that? Second month in Calculus 1, I believe, is where you derive stuff like that, right? So let's look at the second derivative evaluated at 0. Well, first of all, we can come up and this thing goes to 1, right? And this thing goes to 1. The denominator goes to 1. And we are left with phi double prime minus the first derivative squared. And I'm sorry, I should have put a 0 in here. And what is this related to? This is where we get the second moment, correct? And what is this guy? This is the first moment. So we get something with the second moment minus the second moment minus the first moment squared. Hey, remember up here, that's exactly equal to the variance. So that's cool. That's the reason we get that the second derivative, and this is the second property here, the second derivative with respect to omega evaluated at the origin of the second characteristic function is equal to minus the variance. So there's no messing around with computing the first moment and then computing the second moment and then subtracting off the square of the first moment to get the second moment. Also, we'll see it has its mathematical advantages as we go on. We know in electrical engineering that the Fourier transform is not the only transform that we play around with. We also play around with Laplace transforms. And I'm not going to get into Laplace transforms because the Fourier transform is suffices for the stuff that we would like to do. And it does turn out that one can talk about the Laplace transform of the probability density function. And there are kind of relationships between the Laplace and the Fourier transforms. And then the Laplace transform is called something called the moment generating function. So if you ever run across this, you should know, yeah, I've seen this before. It's the Laplace transform of the probability density function. And it's akin to the characteristic function and has the utility. But I'm not going to spend time covering that because I think the similarities are too similar. I guess similarities are similar. These are some of the results of the Laplace transform of the moment generating function, or I'm sorry, Laplace transform of the probability density function, which is called the moment generating function. Now, we also know that we have Z transforms, right? Electrical engineers do Fourier transforms and Laplace transforms. And for discrete time systems, we do Z transforms. Well, if you have a discrete random variable of the so-called lattice type, in other words, the probability masses exist at integers, 1, 2, 3, 4, 5, then you can do a Z transform of the probability mass functions. And this is called the probability mass function for you perform the Z transform on the probability mass function and you get something which you can see at the top of the slide there that's called the probability generating function. And just like the Laplace transform, we're not going to mess around with the Z transforms because everything you can do with the Z transforms and the Laplace transforms, you can do with the Fourier transforms. So let's look at the characteristic functions of some of the common models of probability. Now, don't forget, if we have a discrete random variable, we denote the probability mass with direct deltas. So, for example, for this the Bernoulli random variable, we have one probability mass function here at 1. and that has a probability mass at P. Then we have another one at 0, and that has a probability mass of 1 minus P. So each of these are areas under their Dirac deltas. So this is a Dirac delta with an area of P. This is a Dirac delta with an area of 1 minus P. It turns out you can show very easily that the characteristic function is as is shown here. It turns out for Bernoulli trials, it's not a particularly useful characteristic function, but nevertheless, there she is. There she blows, okay? And I mentioned the Laplace and Z transforms there just for reference. We're not going to dwell on them again. Here is the Bernoulli trials. This is the binomial. And the density function, just kind of as to a review. This takes all of the probabilities and gives them Dirac delta assignments. And this is our transformation from discrete into continuous. Now, what is the characteristic function here? Well, let's go ahead and write that down. Characteristic function is, first of all, as a superscript of the random variable that we're describing, and it's a function of omega. Okay, this is equal to the summation of k over the probability that x is equal to k times e to the j omega k e to the j omega x, or omega k, as we'll see. So that's the characteristic function of a discrete random variable of the lattice type. Lattice type is when all of the probability masses exist and live on integers. Now notice that we can substitute, instead of x, we can substitute k, can't we? Because of the sifting property of the delta function. This delta function only exists when x is equal to k. So we could equivalently put an e to the j omega k there and not change anything, because x has to be equal to k. Because if x is not equal to k, then the function is equal to 0. So let's see what it looks like for this case. This is the summation of over k of n choose k. And what I'm doing is using this expression. This is k is equal to 0 to n of k choose n, p to the k, e to the j omega k times 1 minus p raised to the n minus k. I'm sorry, these deltas go away, don't they? Never mind. There's no deltas in the frequency domain. It's just the probability density function times e to the j omega k. So now in this case, here's one of the formulas that you should memorize. This is called the binomial sum. A little wiggle there. K is equal to 0 to n of n choose k, a to the k, b to the n minus k. So this is a very useful sum called the binomial sum, and is the foundation for the so-called binomial random variable. Because we see that we can write down here I just lumped that e to the j omega with the p. This becomes my A. This becomes my B in the binomial sum. So this is equal to P e to the j omega plus 1 minus P raised to the kth power. Oops, nope. Raised to the what? The nth power. So this is a special manifestation. This is a special manifestation of this binomial sum that we have here at the top, which is applicable for all values of A and B. Now this looks kind of interesting. But before we go on, any questions on this? Okay, we're going to go in for a stretch here. You remember this guy? This was the definition of the characteristic function for a binomial trial, right? Or a Bernoulli trial, I'm sorry, a Bernoulli trial. That's a characteristic function for a Bernoulli trial. Now, keep that in your mind. Well, don't do, I'll actually write it down. So it was 1 minus P plus P to the e d to the j omega. That was the characteristic function for the Bernoulli trial. Does this look similar? It's exactly the same thing raised to the nth power, isn't it? Okay, here comes the hard part of thinking. How do you get the binomial? You get the binomial by doing n Bernoulli trials and counting up the number of successes. So you're adding random variables. You're adding 1 if it's a success and 0 if it's a failure. And so you're adding up all of the successes. What did the characteristic function tell you about adding up a bunch of successes or adding up a bunch of random variables? What do you do in the frequency domain? You multiply the characteristic functions. So we are taking the characteristic functions of the binomial and we are multiplying themselves n times, or we're multiplying themselves by n times, or equivalently raising it to the nth power in order to get the characteristic function for the binomial. Here's something else which is weird. You see this this result here for a binomial. Well, if we add up a bunch of binomials, we get, if we add up a bunch of Bernoullis, I'm sorry, if we add up a bunch of Bernoullis, we get a binomial. Does this mean that this convolved with itself n times? Because remember, if we add independent random variables, we convolve their density functions, right? If we convolve this with itself n times, do we get the binomial? Yeah, we do. So just like with the die, remember the rectangle gave result with the triangle. Here, if we take that, just that 1 and 0, that P and 1 minus P, the binomial random variable, and we convolve itself n times, we're going to get a binomial. So we're starting to see a little trickle. We'll revisit these ideas as time goes on, and but I want to give you a little tease here of, in fact, that we see a lot of this idea of the characteristic function of the convolutions ending up in very elementary probability density functions. Geometric random variable. This is a probability density function. This is the Russian roulette. Russian roulette probability density function. If you put a bullet in a gun with and your probability of pulling the trigger and there being a bullet in the chamber is P, how many times do you have to pull the trigger before the gun goes off? right? So you spin this, you spin the cylinder the first time and you go click, okay, failure, click, okay, failure. You spin it again, click, failure. Every time the probabilities of success is P. The question is, how many times do you have to pull the trigger before the gun goes off? So that's what the geometric random variable is doing. And it is a discrete random variable. And it starts at k is equal to 0. For k is equal to 0, it's P. Why is it P at time is equal to 0? Well, because I guess we're starting to count at time is equal to 0. You always count at a kind of a weird time. Then if it goes off the, this is 0, but actually the pull is 1. This is 1 trigger. And this is 2 pulls of the trigger corresponding to 1. You have to fail the first time, and then you succeed. To have it for the second, the third pull of the trigger, you have to fail twice, and then you succeed. And so this is kind of like an e to the minus t, if you will. This is the equivalent discrete of an e to the minus t as it trails off and eventually goes to 0. So what we'd like to do is we would like to generate the characteristic function for this. So this is going to be the summation of, it looks like k goes from 0 to infinity, of P times 1 minus P to the K times E to the J omega K. That's equal to the characteristic function for this random variable. Is that okay? So we are left with P summation of K is equal to 0 to infinity of 1 minus P e to the J omega raised to the kth power. This is the second formula I think that everybody that is interested at all in engineering mathematics should have memorized. And it's something we took a little bit of time in here to derive. Do you remember that? This is called the geometric series. Hopefully you remember us deriving this in class a few lectures back. This being the case, this is P, and all of this is my alpha, if you will. So it's P divided by 1 minus P e to the J omega. And that looks to be different than we have over here, doesn't it? And I think this is an error. I think this is when the K starts at 1. So I'll let you go ahead and derive that. In fact, I'll give that as a homework to fix this problem. Okay. There's some inconsistency there, and I think that if you give it the eyeball, you'll be able to fix it. It's interesting. I used these slides last time I taught the class, and I guess I didn't derive it because there looks to be an inconsistency. Let me look here very quickly and see if there is an inconsistency here. No, it looks righteous to me. Okay. Here is the Pascal or negative binomial Pascal. And I'm not going to derive it, but it's equal to this. It's equal to the expression that we're given here. I want you to think about this and think about this in relationship to the geometric. This is the Russian roulette thing where how many times you have to pull the trigger before it fires, right? Here, how many times do you have to pull the trigger before it fires? R times. That's what the parameter R is. How many times do you have to pull it before it fires R times? Isn't that just a repeated Russian roulette problem? You pull it once till it fires, you pull it again till it fires, you pull it again till it fires, and you do it for R times. If you add all of those up, that's what the Pascal or negative binomial is. And so again, you're adding up a bunch of random variables. So if you look at this, and you look at my previous result, let's assume the mistake here for purposes of illustration. But you notice the geometric random variable raised to the rth power is equal to this expression. So again, we have this manifestation of random variables adding corresponding to the characteristic functions multiplying. And if you have the same random variable and you repeat that random variable n times, you're simply taking the characteristic function and raising it to the nth power, because all of the characteristic functions are identical. Poisson random variable. This is the Poisson random variable. I love this one because it's the only place in kind of cool math where I see an e to the x, and it kind of occurs unnaturally. This is another summation that you should know, is that e to the x is equal to the summation. Let me use k here. That's the Taylor series expansion for e to the x. Is that okay? And this is the reason that we know. Well, let me just derive the characteristic function for the Poisson. For the Poisson, we have the summation of k is equal to 0 to infinity, lambda k over k factorial, e to the minus lambda times e to the j omega k. And we can play around with that a little. It's e to the j minus lambda summation of k is equal to 0 to infinity. And here's where it comes in. It's lambda times e to the j omega raised to the kth power over k factorial. In other words, I've just taken the e to the j omega k and lumped it with the lambda. And this infinite sum is recognized as the Taylor series expansion for e to the x, except that we don't have e to the x. We have e raised to the lambda e to the j omega. Isn't that cool? We get an e to the e. By the way, anytime you derive a characteristic function, you can do a sanity check. What is the characteristic function evaluated at 0? Always equal. It's equal to 1. Is that true? That's always true. We've shown that that's always true. If we take this expression and set omega is equal to 0, what do we get?
Would be e to the minus lambda times e to the lambda.
Which is?
I think it should be 1.
It's 1. E to the lambda times e to the minus lambda is equal to 1. And I've lost, whoop. Yeah, for omega is equal to 0, that becomes this, and e to the minus lambda, e to the lambda is equal to 1. So that's a sanity check. We can actually go back. What about for this case? What happens when omega is equal to 1? The top becomes p, doesn't it? because e to the j0 is p. What does the bottom become? 1 minus 1 minus p times 1. Correct? And of course, that's equal to 1. Whoops, this is omega is equal to 0. So we see in all of these cases, we kind of pass a sanity check, a criterion for the characteristic function. It better, evaluated at 0, always be equal to 1. Let's see, what about the binomial? Let's look at this thing at omega is equal to 0. What is it for omega is equal to 0? It's 1 minus p plus p raised to the nth power, which is 1, right? So we can see all of these characteristic functions add up to 1. So the characteristic function is kind of a cool way to think about random variables. Some other ones that we can talk about is the Gaussian. And I'm not going to derive the the uniform. Here's the uniform random variable. This is where it's uniform over the interval from A to B. So that's the density function here. And if that's the density function for uniform between A and B, this is the characteristic function. Now, I think in electrical engineering, we're more used to the idea that a rectangle Fourier transforms to a sinc, right? A sine x over x. That's everybody's first Fourier transform. And if you manipulated this a little bit, you would get a sinc. The Gaussian, this, believe it or not, is one of the most difficult Fourier transforms to derive. But it turns out the Gaussian is always our friend in probability. Gaussian just has incredible properties. For example, with the central limit theorem. Everything goes to a Gaussian, as we'll show. And it turns out that the Gaussian has an interesting property that it is its own Fourier transform. If you Fourier transform a Gaussian, you get a Gaussian. And that's what we have here. We have a Gaussian with respect to x. Here we have a Gaussian with respect to omega. Here's the exponential random variable. This is a very easy one to derive, and I won't go through the time to do it because I would expect everybody can do the exponential random variable and generate the characteristic function for that. It is a very simple integration. As long as you know how to differentiate e to the x and integrate e to the x, you should be able to get this. The Laplace, which is the two-sided exponential, as a characteristic function which looks like this. You know what's interesting about the characteristic function? It has a Cauchy shape. We talk about the Cauchy random variable, and we can also talk about a Cauchy shape, which is like a 1 over 1 plus x squared sort of shape, very fat tails. And it turns out that this has a characteristic of a Cauchy curve as the characteristic function. Very interesting result. The gamma random variable is one that we talked about when we introduced this with relationship to Vasco da Gama, if you remember. I'm going to give this, and this turns out to also be a autoconvolution of a more elementary result. In fact, I want you to look at this. This is fascinating. Here is the characteristic function for the gamma, right? Just accept it for now. What's the characteristic function for the exponential? Lambda over lambda plus j omega. Here we have the same thing. We have the same thing except raised to the 8th power. So if one adds up a bunch of exponential random variables, one is going to get a gamma random variable, which is kind of cool. Because again, if you add independent random variables, what do you do to your characteristic functions? You multiply them. If you have a bunch of identical random variables like exponential plus exponential plus exponential plus exponential. So you're doing a test, say a test in reliability. You want to see how long this thing lasts, how long this thing's lasts, how long this thing's lasts. And you add up those random variables, you're going to multiply their characteristic functions. And so what we're saying here is that the characteristic function for an exponential, a single experiment, so if we have a number of experiments, we put something on test and it fails here, okay? Then we put something on the test and it fails here. Let's call this X1. This is the outcome of X1. This is the outcome of X2. Say we put a light bulb on test. We put a light bulb on test, it gets out here to X1 and it fails. We put a light bulb on test, same batch, and it goes out here to X2. And then we go out here and we do another one and it lasts X sub 3. So that's the time each one of these lasts, right? And so what we're doing is we're forming a new random variable, which is the summation of X1 plus X2 plus X3. Are these random variables independent of each other? Yes. In fact, that's usually the characterization of independent random variables, is that they're outcomes on repeated tests that are independent of each other. They are independent. So therefore, the characteristic function of the random variable is equal to the characteristic function. Let's call this x3. So the sum of 3 is equal to the characteristic function of each of these multiplied together, which is in this case cubed, right? Since there's 3 of them. So therefore, it would be a gamma random variable if we did 3 tests and we knew what lambda was with a parameter a is equal to 3. This is really cool and a very cool and interesting result. And I want you to be thinking about that. I'll be assigning some homework problems and hopefully get us to the point where we can go back and forth with some questions to clarify this, because this is really important stuff. Okay, any questions at all? Okay, so thank you very much. And until we talk again, be of good cheer.